Hi guys, so here's video 2 for today. We're going to start with the intro to the entire chapter 8, and then we'll go into 8.1.1 binomial distribution. So this whole chapter, what it's going to be about, it's going to represent something like this situation here. So take a chance to read through it, think about it, answer some of those questions, get paused, and then come back when you have that, and we'll go through it. So each question has choices A, B, C, D. On average, how many would you expect each student to get correct? Well, if there's a 1 in 5 chance of them getting it correct, that's 20%. So if there's a 20% chance of them getting it correct, we probably expect them to get about 20% right. So 20% would be 2 out of 10. So we probably expect them to get about 2 right. Make a graph of what you'd expect the distribution to look like. Now, I don't know what you did. Hopefully you did something like this. We expect most students to get 2 right. And then, maybe some got lucky and got 3, or some got a little less lucky and got 1. Some probably got none, some probably got 4, and maybe some got really lucky and got even more than that. But you'd probably expect to see something like this. What would you expect it to look different if there's only 4 choices? Yeah, a little bit, because then we expect them to get 25% right, and so maybe the whole graph would shift up just a little bit to about 2.5 questions. How could we simulate this? We could simulate it if we said 1, they got it correct, and 2 through 5, they got it wrong, and we could do 1, 5, pick 10 questions, and we could see how many they got right, and we could do that several times. So this is a very typical situation that we're going to look at in this chapter. How is it different from last chapter? Well, many of these situations only have 2 outcomes. So in this situation, either you're going to get the question right or you're going to get it wrong. A lot of outcomes: you have heads, you have tails. You have a boy, you have girl. You make the free throw, you miss the free throw. You pass the test, you fail the test. It's a good part, it's a bad part. So this whole chapter is going to focus on that kind of situation. 2 choices, either good or bad, success or failure. So section 8.1 will be all about binomial distributions. Binomial, bi means 2, bicycle. So binomial is two choices. This is section 8.1. Geometrical is 8.2. So in section 8.1, here's an example. Nikki is a 60% free throw shooter. In the season, she shoots an average of 75 free throws. So now we would expect her to make about 60% of those. But the questions are, what are the chances she makes exactly 50 out of 75, more than 50, less than 40, between 45 and 50? Well, these are the kinds of questions that we can answer at the end of this section. We can answer all of those exactly. I can give you the probability for all of them. Now, the most important part, what you're going to do today, is you just have to identify if it is a binomial setting. So to be a binomial setting, you've got 4 criteria. The first, each observation has to be a success or a failure, a heads or a tails, a win or a lose. But there can only be 2 outcomes. There has to be a fixed number of observations. So there has to be 75 free throws, or 10 questions on the test, or there's going to be 5 children, but it has to be a fixed number, else we cannot use binomial distribution. Everything needs to be independent. So each free throw she shoots has nothing to do with the last, or each coin you flip has nothing to do with the last. And the probability of success, which you will call P, has to be the same every single time. So every single time, there's a 60% chance she's going to make her shot, or a 20% chance she's going to get the question right. And obviously, if she's not going to succeed, she's going to fail. So the book likes to call failure, they like to call it 1 minus P. We're going to refer to it just as Q. So P is for success, Q is for failure. Okay? So consider the multiple choice test example. If we think about that one, let's stop right here. There was only 2 outcomes. Either you're going to get the question right or you're going to get it wrong. There was 10 questions on the test. Every question, you still had an equal guessing chance from question to question. And every 0.1, there was a 0.2 probability you're going to get it right. So if those 4 conditions are met, then just like last chapter, how we define an x, y, z, our random variable is going to be a binomial random variable. And the probability distribution is called a probability or a binomial distribution. So same as last time, we could still make that distribution. We could still make what's the chance of x, what's the chance of p of x. It's still the same idea that way. It's just now it's binomial. And if I want to describe it very quickly, it can be n comma p. So for example, with the multiple choice test, there were 10 questions. Each question had a 20% chance of being right. And you can read through this box, but it basically says what we just talked about. Okay? Most important skill for using binomial distributions is, can you figure out if it's a binomial situation? And there will be a couple of these on the AP test, so the quicker you recognize it, the easier it is. So, if both parents carry genes for O and A blood type, each child has a 25% probability of having type O. Consider the number of O blood types among 5 children. So go through the 4 criteria, fill them in, tell me if it's yes or no, hit pause, and then we'll do it together. So first criteria is that it's either a yes or no, and that is true. So it's either yes, it's type O, or no, it's not. So that criteria is met. Second criteria is that there's a fixed number of observations. That comes with the 5 children. We're only looking at those. Fourth criteria is that every child is independent, and that should be one child's blood type doesn't determine the next. And then the last criteria is that the probability stays the same, and every child has a 25% chance of getting type O. So this is a yes. So do example 2. Hit pause, let me know when you're ready. So a card is dealt from a deck can either be red or black. Consider the number of red cards among the 10 cards dealt. So, yes, it's either red or no, it's not red. So that criteria is met. Fixed number of observations, yes there are. There's 10 cards dealt. Each card is independent. No, that is not passed. Unless they put the card back in the deck and reshuffle, once you draw a card, it changes the probability of the next card. Probability of next card. So it fails for 2 reasons, because they're not independent, and because they're not independent, then number 4 changes because P is not fixed. It's going to change every single card you draw. Okay? So this is a giant no. This says, so I think that's the end of 10. I'm going to scroll back up. So this says, choose a simple random sample from n-size population with a p chance of success. When the population is much larger than the sample, count x of success in the sample is approximately a binomial distribution. What this is really saying is this example here. So an engineer samples 10 switches out of 10,000 switches. Unknown to the engineer, 10% of the switches are bad. Consider the number of switches in the sample. So right here, this passes. It's either bad or good. N is 10,000, so we're good right there. Independent. Each switch is independent. It has nothing to do with whether the next one is good or bad. But does the probability of pulling a bad one stay the same? So if 10% of the switches are bad, that means that 100 out of the 10,000 are bad. And every time I pull one, so let's say I pulled one of the switches out, well then only 99 out of the 9,999 left are still bad. or let's say I didn't get a bad switch, then 100 out of the 9,099 are still bad. So P does change, but this is the idea that they're trying to tell you here. When N is really large, the idea that we hate about this class, close enough. The difference between 100 over 9,999 or 99 over 9,999 is so stinking small that we don't care. It is close enough to being a 10% chance every single time that we can go ahead and use this method, and it's not going to change our answers enough to care about. So, and then I'm sure you're going to ask me, well, how do we know if it's large enough? I don't have the perfect answer for that, but it's going to be obvious. It has to be a very large number. It can't just be out of 100. It can't just be out of 20. It's got to be in the thousands or higher before we consider it being close enough. So if you have any questions, get on Google Hangout, let me know what they are, and I'll see you Monday.